I wanted to test Chat GPT. In particular, I wanted ChatGPT to derive, if possible, the commutation relation for a real scalar field that in quantum field theory usually one comes across, and it can be written as you can see here. So the commutation relation between the field phi and pi, which is canonical momentum, and it can be defined like this. So it's the derivative of the Lagrangian density with respect to phi dot, and it can be calculated to be equal to phi dot. So the Lagrangian is also introduced here, the Lagrangian for a real scalar field. It's also related, if you want, to Klein-Gordon, the Klein-Gordon equation, and so on. And usually one comes across this in quantum field theory, in courses on quantum field theory, and this is actually the starting point. So it's some kind of postulate that one starts from, and then all the other derivations are a result of this expression here. So this is a starting point. Now let's see if ChatGPT is able to derive this result from a path integral. I have tested it, and it is quite surprising to see that the calculations are actually sound and they seem accurate. In particular, we start from a Lagrangian in a d plus one dimensional scalar field, and the Lagrangian density is an integral over the volume in this d dimensions of space. So d plus one dimensional scalar field means that we have d dimensions of space and one dimension of time. And the Lagrangian can be obtained like this by integrating this expression, which is not written using tensors, but it's the expression related to Klein-Gordon, depending also on how the potential here is defined, V of phi. I will not get into all the details. I'm assuming that you are familiar with Klein-Gordon equation, for example, and you know how to write the Lagrangian density of a real scalar field. So the momentum density, if you want, can be obtained by taking the derivative, and this is a functional derivative with respect to phi dot of tx. This vector x here is d-dimensional and t is just a scalar. It's the parameter related to time. And if you calculate this derivative, it's quite simple to see it also from this expression that we get phi dot of tx. Then ChatGPT slices the time axis in this manner. So it's a simple time slicing procedure here. So instead of considering the continuous field phi of tx, it considers phi sub k of x. So in this case, it only discretizes the time variable, but space remains continuous so far. So it can also be written as phi of t sub k x. And the discretized action can be rewritten like this. So ChatGPT emphasizes the so-called kinetic part of the action, which is this important part here. So you can see that we have a dt, delta t, in the denominator because it comes from discretizing this derivative, basically. So this derivative phi dot squared contains a delta t squared in the denominator, but when we consider the action, remember that we need to integrate the Lagrangian also with respect to time. And once you consider all the products, you get delta t in the denominator because it comes from multiplying delta t coming from the action. And remember that we have delta t squared in the denominator of phi dot squared. So that's why you get delta t here. And I will not get into all the details, but you should follow the procedure. And then we also have a path integral written in this form, and then we have all the products over k, and then we also have a limit as n goes to infinity. So n goes to infinity is important because the time slicing should be made in such a way that when this n goes to infinity, we get back our continuous result, assuming that this limit exists and so on. Then what else do we have to consider? So we have this second part of the answer that starts from this from this result. So 0 equal to this. So you can see that we have some kind of path integral as well. We integrate over d phi the fields, and we have a functional derivative of phi sub k multiplied by e to the I over h bar s of phi. So is this true? Actually, yes, because when you integrate a derivative, you have a boundary term. So we assume that the boundary term vanishes, right? Even if this is a result that is related to functional differentiation, and it is a little bit more complicated than usual derivatives. But you should understand that this expression holds. So it makes sense to write something like this, and this is a starting point for a derivation. So we can take the derivative of this product. So the product, when you take the derivative of a product, you take the derivative of the first term, and then you multiply by the second term, and then you have the first term times the derivative of the second term. So the functional derivative here of phi sub k of x with respect to phi sub k of y gives rise to a Dirac delta. So in the discrete version, instead of having a Dirac delta, you have a Kronecker delta. If you also discretize the space variables here, but we have not discretized the space variables, so here we actually have a Dirac delta. And then by using this result, Chat GPT rewrites the integral here by taking one of the two terms on the other side, and then ChatGPT calculates the derivative of the exponential e to the I over h bar s. It can be calculated quite easily. There is nothing major, and it rewrites the term like this. So we have a derivative of the action with respect to phi sub k of y, and we still have e to the I over h bar s. And then when you rewrite the integral here, we can see that we have an average of this term equal to the one that you see on the right, and the average can be calculated by using path integrals. So you should be aware of how to do that, how to calculate averages using path integrals. And now the final part of this answer considers the term, so the functional derivative of the action with respect to phi sub k. So how to calculate that? How can we calculate that? In order to calculate that, we need to write down the kinetic part of the action, because this derivative will only act on the kinetic part of the action, and it is actually quite intuitive that it should be so, because you can see that here we have a kinetic part, the kinetic part here, and then here on the right we have terms. So we have the gradient of phi squared plus a potential, but these terms are multiplied by delta t. So when delta t goes to 0 in the classical limit, this term will be small, whereas this one here will prevail. It will be dominant, and therefore we can only consider this part. That's why we are interested in the kinetic part. So the derivative will have to be calculated here on this term that's discretized in time. Phi k, you can see that phi k considers the discretization in time. Remember that. So we need to calculate the derivative of such a term, a functional derivative. It can be calculated with simple rules, which are similar to usual rules that you have in calculus. And here you see the result. You have a Dirac delta first, and then when you integrate over the Dirac delta, you get something of this kind. Minus 2 phi sub k plus 1 y minus phi sub k of y. So you can calculate the derivative, and then you replace the result in here, so that this is what you get. You can see that ChatGPT writes another term that's proportional to delta t, so it's dominated by delta t. So when delta t goes to 0, this term here goes to 0, and we can neglect it. And then, so you can see that ChatGPT introduces the discrete canonical momentum. And for example, you can write it like this. So you can write a momentum of the kind pi sub k minus, and the minus is related to the fact that we calculate the difference phi sub k minus phi sub k minus 1, and then we have a pi sub k plus. That's like a term that we have, so it's like a limit from the right. So we have a phi sub k plus 1 minus phi sub k. Both of them are evaluated at y, and the only discretization is in time. So we can rewrite basically this derivative, this functional derivative like this, by using discrete canonical momenta, and by replacing this expression into the previous average that we see here, what we obtain is this average. And this is actually related to a time-ordered expression of this kind. So you can rewrite everything like this, which is something very, very similar to a commutator. So I will not read all the steps, but what you get indeed is a commutator between phi and pi. And that's exactly the result that we expected. So actually, ChatGPT was very precise in giving the answer. Of course, the answer also depends on how you formulate the question, and now I will not show you how you how I formulated the question, but it's pretty incredible to see how amazing the changes that were made to ChatGPT over the previous years are. So if you started using ChatGPT, for example, in 2023, and indeed that's the year in which I started using it, and that was actually the start of this revolution dominated by artificial intelligence, at least on a large scale. But now, as I'm recording this video, it's 2025, so 2 years have gone by, and the changes that were made to ChatGPT are quite interesting, quite amazing, in my opinion, not just in mathematical terms or in physical terms, but also in logic and other types of problems. It's definitely incredible. So I will not philosophize. I will not discuss any philosophy behind artificial intelligence in this video. But to be honest, it's surprising to see the level it reached. And then I also decided to ask ChatGPT to do another derivation of the same expressions, but by calculating actual path integrals. So without using those derivatives, those functional derivatives that you saw earlier, but I asked it to do the calculations by actually tackling the path integral expressions that we have. So we have Gaussian integrals basically. So in this case, in this answer, ChatGPT divides the time axis into slices as before. So there is a discretization in time, but there is also a discretization in space, as you can see here. So here we have the notation phi sub k up, and then we have also a superscript n. So I can say for simplicity phi nk. And you can see that it is a discretization of the function phi of tx. So we have phi of t sub k xn. And then we have a fully discretized action. So we have a kinetic term here. And then we have the other term that's proportional to delta t. And we know that this term will not be important in the calculation of path integral. So we will actually be interested in the kinetic part. You can see that we also have this scalar A, and the scalar A is a cell volume. So it's the unit of volume in our grid of points, basically. So it is something that in the continuous limit should go to 0, this little a. And so here ChatGPT also explains that this term, so with the gradient on the lattice, lat here stands for lattice, and phi of k, it's the special gradient basically discretized, and it will not dominate for short time steps, as we will see. So the path integral can be written like this in this case, where we have discretization both in time and also in space. And then the kinetic term will be something of this kind. So here, pay attention that we have two indices. We have n, which is the index in space, and then we have k, which is the index in time. And for example, if we fix n, one term contained in the action will be of this kind, simple algebra. Then Chat GPT defines, in order to simplify the notation, it defines this alpha here as a to the power d divided by delta t, and then we have b sub n, which is defined like this, and then the phi nk dependent part in the exponent up to some constants is of this kind. So it's an intelligent way of writing the expression, because then we will have to take basically not derivatives, but we have to integrate over the generic phi and k, and it's an intelligent way of writing it, because then it will be easier to do the calculations. So we also have another part in the action, and I will not bother, let's say, studying every detail of this expression. It's not complicated, but the important thing to notice is the fact that we have delta t. So this part of the action is proportional to delta t. So when delta t goes to 0, this part will not be important. So only the kinetic part will dominate, basically. So indeed, we have to study this part of the action. So we have a leading Gaussian integral. So the Gaussian integral will be related to such an expression. So here you can see that we have integrals that contain exponential of this expression here. So they are proportional to this. And integrals of that kind can be calculated quite easily, because they are quadratic. So we have an exponential of something that's quadratic over the field, and then we also have a linear term. So we can complete the square as it's usually done for path integrals, and they can be calculated quite easily. So I will not bother following every step. It's quite simple, actually, if you know how to calculate Gaussian integrals. So that can be done, and you can see that we have an expression of this kind. And anyway, you can see that for one lattice site n, the normalized leading order distribution is of this kind. So we indeed have exponentials of this kind. And completing the square, we can rewrite those integrals like, those exponentials like this. And then we can take the expectations or the averages. So I'm using the word expectation as a synonym of average without being too precise. But you can see that, for example, the average of the field phi will be b over 2. So when you complete the square, you can see that indeed inside the exponential we have phi minus b over 2 squared. So you can see that the average appears in here. So you simply have to calculate the Gaussian integral, even if there is this imaginary unit, that can be done quite easily, and you get b over 2, for example. And then you can calculate also the variance of this variable phi minus b over 2 squared, and you can read the variance from this part of the expression, I alpha over h bar. In particular, that's equal to 1 over 2 sigma squared, where sigma squared is the variance. So if you rearrange the equation to find sigma squared, you can rewrite basically the solution for sigma squared, which is I h bar over 2 alpha. So that's quite easy. You have to calculate basically this average if you want, or if you are familiar with the Gaussian integrals, you can easily see that the variance can be written like this. And therefore, from this equation, you can derive the average, or if you want, the expectation of phi squared, which is this. And then we can also define the discrete momenta. So we have pi sub k minus, so the minus indicates that we start from phi sub k and then we subtract phi sub k minus 1. So you can see that we also have the other index n. And this is, let's say, very similar to what we did in the previous answer of Chat GPT. And then here we have pi plus. So we have phi sub k plus 1 minus phi sub k. Then we have, so ChatGPT considers their subtraction. So we have pi minus pi plus, and it is rearranged like this. And when we take the expectations, so when we take the expectations, it's quite easy to see that we get basically. So here you can see that we have this expectation will be a combination of the expectation of phi squared and phi. And the calculation leads to I h bar over alpha. That's simple algebra. And then here we have this expectation equal to I h bar divided by alpha delta t. Remember the definition of alpha that was given earlier by ChatGPT. So alpha was equal to a to the power d divided by delta t. And therefore, this result can also be written in this form. I h bar over a to the power d. So this is the discretized version. And in particular, this is also the expectation when n here, so here we have n, and here we have n, so both in the field phi and in the canonical momentum, we have the superscript n. If we, for example, change the superscript in pi, in the canonical momentum, we change it to m. It is quite intuitive to understand that in that case, when we take the integrations, we have independent variables, and therefore, if m is not equal to n, the average will give us 0. So it can be done more rigorously, but it's quite intuitive in my opinion, and therefore, when you do this calculation, a Kronecker delta will appear. So in this case, we have a Kronecker delta because both space and also time are discretized. So in this case, the letters, so the indices n and m are related to space. So this is the discretized version, and we can take the limit to go into the continuous version of it. I will skip this step 5 because it's not necessary to go through it here. I want to go to step 6. And as I said earlier, the part proportional to delta t will be negligible, so we can already neglect it. And when we go to the continuous limit, so this was the result in the discrete case, this delta nm divided by a to the power d will become the Dirac delta of x sub n minus x sub m. And in particular, x sub n, for example, can be simply called x, whereas x sub m can be set to y when we go to the actual continuous domain. And in particular, let me also comment that this a to the power d here only appears in the discretized version because it is important to normalize the volume. So in particular, if we integrate over a volume and the volume of a cell, so if we integrate over the volume of a cell in the continuous case, and also in the discrete case, we have to normalize it, so we have to get 1. In particular, we have to integrate over a volume equal to A in the discrete case because that's the smallest volume. So we cannot integrate over a volume that's smaller than a single cell. It's part of the discretization process. But when we go to the continuous case, then we have to be able to integrate over even a very, very, very small volume, infinitesimally small. So in that case, we need to use the Dirac delta. So when we integrate over a small volume, even if it's a very small volume, the Dirac delta will have a volume equal to 1, basically. So that's the intuition. And in the continuous case, you can write an equation of this kind, in particular this can be written as a commutator. So we basically reobtain the commutator, and that's the idea that is behind the path integral of the Lagrangian of a scalar field, related to the Lagrangian of a scalar field. And that's how, from path integrals, you can find the commutation relations, the usual commutation relations for scalar fields. And in my opinion, this is actually very interesting because ChatGPT gives a very accurate answer